You have 3 identical beakers sitting on a desk. They're all filled with a completely clear, odorless liquid. Chemically, they are entirely different. One holds a sugar, one a starch, and one a protein. Without a multi-million-dollar mass spectrometer, your eyes are useless here. At a macroscopic level, these molecules are indistinguishable. The biochemical assay is the solution to this problem. These tests translate hidden molecular shapes into macroscopic color changes that we can actually see. Biological molecules possess functional groups, specific atomic arrangements acting as triggers. When exposed to the right reagent, they lock together, triggering a reaction. Running our unknown liquid through these tests creates a deductive pathway, eliminating possibilities one branch at a time until the identity remains. In the lab, we don't just observe. We deploy specific reagents and apply heat to trigger reactions, forcing these molecules to produce a physical signal of their identity. Our first objective is to categorize the unknown sample into one of the major macromolecule families. We start with Mollis's test, dropping in a solution of alpha-naphthol, followed by a dose of concentrated sulfuric acid. The acid acts as a dehydrating agent. Almost immediately, a distinct, vivid purple ring forms at the junction of the liquids. That ring proves our sample is a carbohydrate. The specificity of the test is key. If this were a protein, Mollis's reagent would do nothing. Protein peptide bonds require the Burette test to produce a violet color, or a chemical called ninhydrin to detect free amino acids. We have successfully placed our sample in the carbohydrate family. However, the exact type of sugar is still hidden. The next step is to determine the size of the molecule. We need to know if we're dealing with a massive, complex chain like a starch, or a simple sugar. We test for size using the iodine test. Triiodide molecules are linear, and they physically slip inside the hollow core of a coiled starch molecule, trapping themselves to create a deep blue-black color. When we add iodine to our sample, the liquid remains clear. The molecules don't have that coiled structure, which eliminates complex polysaccharides from the investigation. Now we measure reactivity. We introduce Benedict's and Tollin's tests to check for a free aldehyde or ketone functional group. If it exists, the sample is a reducing sugar. In Tollin's test, the chemical reaction reduces silver ions into solid metal. A reflective silver mirror rapidly coats the inside surface of the test tube. Between the brick-red precipitate of the Benedict's test and this silver mirror, we have our proof. The sample is a reactive reducing sugar. To find its specific atomic arrangement, we have to look closer. We use Barfood's test to separate single-ring monosaccharides from double-ring disaccharides. This test relies on the raw speed of the reaction. Our sample reacts in under 2 minutes. That rapid timing proves it is a stronger reducing agent, isolating it as a monosaccharide. Next, we use Bial's test to count the carbons. The sample produces a muddy brown precipitate, confirming the molecule is a hexose, meaning it has 6 carbons, rather than a 5-carbon pentose. For the final identification, we use the ozazone test. This reaction locks the sugar into a rigid, macroscopic crystalline lattice. We add phenylhydrazine, which binds to the specific geometry of the sugar. Different sugars form uniquely shaped microcrystals, like thorny balls or powder puffs. We are looking for needle-shaped crystals. At exactly the 5-minute mark, yellow needle-shaped crystals bloom in the test tube. The combination of shape and timing provides a definitive identification. This liquid is D-glucose. We started with a clear liquid. By using specific reagents and observing precise reaction times, we successfully mapped an invisible molecular geometry. These abstract benchtop reactions solved real-world medical problems. They provided the practical evidence needed to build modern clinical diagnosis and nutritional science. Long before modern electronic sensors, testing for reducing sugars was the earliest reliable method for doctors to detect glucose in the urine of diabetic patients. By exploiting these molecular weaknesses, chemistry lets us see what the eye cannot, translating microscopic structures into a series of predictable, visible signals.